Hey, Algebra 1, Catlin here with your help for Lesson 2 here in Unit 5 as we're continuing to look at exponential functions and just how they're different from these linear functions that we've been doing beforehand. A lot of you missed today, so I'm talking to many of you, hopefully, that are trying to stay caught up. We looked at these tables using um, Excel spreadsheets, and I already closed them out, or I'd pull you up what we did in class today. But it was tables just like this where we saw these patterns that as years passed, population, or in our case today in class, we were looking as years passed, these number of stores that were opening up. So this particular one is talking about cat population on these two different islands, Meow Island and Purr Island, which is hilarious. But these tables are showing growth over time over the first 4 years of the island being there. Obviously, there's two cats that are one male, one female, and they start to reproduce, and then the numbers just kind of go crazy on Meow Island. I guess things are um, are really cooking there on Meow Island, and not so wonderful over on Purr Island. There's not as much growth, and so we're looking at the difference between the growth and describing mathematically as precisely as we can uh, how the cat population is changing. So words that we're starting going to start throw around are words like exponential. Um, and words like linear as we're talking about these types of growth, but we can also discuss them in forms of equations that we can write of how we can take the year and get to the number of cats. And that's really what we're shooting for in these problems. So let's start with that. Something that we really discussed in class today was the challenging thing for Meow Island is that it grows so fast. To find a rule to take the year and get to how many cats are gonna be on that island is difficult because we haven't done anything like that before. But let's start with one that we have done before is writing a rule for this one. So let's say that years are Y and the number of cats on the island. I take that back. Let's redo that. Let's say that the number of cats on the island is Y and the years are X. We'll go that route for both of these. If we're doing this one, and we wanted to make a rule for getting there for these, then what we could do is we could look at the change per year, and we could notice that they're just there's four more added to the island every year, right? It's pretty basic, just a new family showing up, right? Family of four is coming in, moving into the island. So we can take that difference every year, and that's really going to be like our multiplier for our rule. So if I want to get from years to per island, how many cats are on per island, I could use a multiplier of 4. Well, that works pretty good, but they're still gonna be falling short because 4 times 4 is 16, 3 times 4 is 12, 2 times 4 is 10, 1 times 4 is 4, and 0 times 4 is 0. They're always falling too short. So if we were gonna write an equation for this one, we would simply write y equals 4 times the number of years, but we have to add those extra 2 because we're always falling too short. These are equations that we've been writing for a while, and they're very we're accustomed to them. But this other one is a little more difficult to write an equation for because it's not growing at this plus 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 rate. Okay, it's not a sequence of addition, it's a sequence of multiplication. They're tripling in number every year. And that's something that you could write in your description is that they're tripling, right? You could also write something like it's growing by factors instead of growing by, differences, which is what we put in our table today. But if we have this repetitive multiplication, we don't have multiplication is not repetitive multiplication. Multiplication is repetitive addition, which we see here. That's why we have 4 times x, 4 plus 4 plus 4 plus 4. But repeated multiplication brings into the idea of using exponents because you're multiplying the same thing over and over and over and over again. And that same thing you have to think is what number are we tripling every time, right? What number did we start with? And that's really where we got into our discussion today because the base idea for the exponential equation looks like this, where you have y equals, and you're going to have your start number, kind of where you begin. With the genie problem, it was a penny. And then when we did our problem today with the stores, it was 5. And with this problem with the cats, year 0, we're starting with 2. So our start number would be that. You take your start number and you multiply it by the factor at which you are sequencing your growth. So times 3 would be our factor in this case. And then you take that to the power of, whatever your variable is. So this is kind of like the setup for the exponential function of doubling, tripling, quadrupling growth. This is your basic setup for the function. So when we write it for it like this, we could say our start number is 2, and we multiply that by our factor, which is 3, and we take that to the power of x. So this equation right here, we can plug in 0, 1, 2, 3, and 4 in x's place. And what it's going to do is it's going to multiply out and tell us how many cats are on Meow Island. Watch, it'll work. We'll do a couple of examples. Let's try 2. Let's put 2 over here in x's place. If we do that, y would equal 2 times 3 squared. Follow your order of operations. You don't multiply first, you exponent first. 3 times 3 is 9, and 9 times 2 is 18, which is what we get there. If we put a 3 there instead, it would be 3 times 3, which would be 27, and 27 doubled would be 54. So you can see that this expression or this equation will work for all of these years, even if we put 0 there. I don't know if you've tried it before, but any number to the 0 power is equal to 1. So that would become 1 times 2, which is 2. So as we look at some of these exponent rules, that'll help with what we're going to be doing lately. But you could say on Meow Island, we are tripling in population, and on Per Island, we are adding 4 new cats every year. And precisely with mathematics, we can write these equations to show how the growth is changing. And we're going to investigate this much more, but we're just kind of scratching the surface with these exponential functions where we have variables that are in the exponent and not just, somewhere else in the problem. So think of, your y-intercept was here with 2. Now we talked about this today. Your y-intercept is actually this start number, and your factor of how many times you're multiplying it to get to the next one is at the bottom of your exponent to a power of the number of times that it happens in years. So we will see more of this for sure. I'm sorry this video is a little long, but I'm trying to keep all my people that are missing caught up. Later, guys.